Let's take a look at what you had. Now, another way to look at this, remember we looked at this algebraically to see where your domain restriction was. If you think back to your domain restrictions, remember when we had radicals and we said underneath the radical could not be a negative. So we took what was under the radical and we said greater than or equal to 0. If we know that your log cannot be a 0, cannot be a negative, we could take what's inside this argument and set this greater than 0, and we can find your domain. So if you struggle with finding your domain, this is a very good way to do it. Graphically, it's far easier without the calculator because you actually can trace your steps here. If this and LNs and logs work the same way, your natural log is kind of like a base 3 log. So it's kind of just same direction. It still has the same attributes as before. Your domain was from 0 to infinity. Your range was all real numbers. Your asymptote, again, remember, is x equals 0. And your x-intercept is 1, 0. So if we're going to the right, you're going to add 1 to the domain because you're moving it over. So your domain becomes 1 to infinity. And algebraically, we saw that. The range stays the same. My intercept moved over 1. So this guy moves to 2, 0. Now we have to find this guy algebraically. So algebraically, when we look for an x-intercept, we set y equal to 0. If it's easier at this point, switch this around. Put it this way. The base of an ln is e. E to the 0 equals x minus 1. Anything to the 0 power is 1. So that'll help you find your intercept. Make sure you name your transformation. Horizontal shift 1 right. Okay?
Wait, why did you do E?
Well, because we always find our intercepts algebraically. So even though we spotted it that moved over 1 unit, we were able to see where it moved. Algebraically, to find an x-intercept, you set y equal to 0. So when we go to your equation and we set this equal to 0, if this had been a log base 2, I would flip this to an exponential equation, right? Probably easier to put it on this side. I think it looks better this way. Watch. Whether you use that or log equals exponent, log equals exponent always works. The base 2 to the 0 equals x minus 1. Anything to 0 is 1. Then add 1. Now when we get to an ln, what's the base of ln? E. So same result. E to the 0 equals x minus 1. If I gave you this, what's the base on this log statement? What's the base on this log statement when the base doesn't show up? 10. So wouldn't it be better for me to write my 10 in here? 10 to the 0? Right? I have to put my 10 in there. So with an ln, you have to put your E in there. And that'll work out okay. Remember your intercepts, you have to find them algebraically. You can look for a y-intercept because we won't have one because that's where your asymptote is sitting right now. If we moved to the left of it, maybe, but not to the right of it. You okay with those? Stop me if you have any questions. These are important that you get these. Okay, the next one. If your x is going from positive to negative, move your finger from positive to negative. There's your reflection over your y-axis. So just reflect this in your y-axis. If you use your rule that negative x has to be greater than 0, if I divide by a negative 1, I flip the sign. And my domain says x is less than 0. And I can kind of see it here too, right? Negative infinity to 0. There's my domain of my transformed log equation. Whether I use log, whether I use ln, it is the same exact thing. Because an ln, even though it's your natural log, is the same as a base 3. Okay, find your asymptote. Did it change by reflecting it over the y-axis? No. I point, flipped right over to here, negative 1, 0. We need to find this algebraically. So let's set y equal to 0. If it helps, put it this way. What's the base of an ln? E. Good. E to the 0 equals negative x. Anything to the 0 is 1. And how do I solve for x? Just divide by negative 1. Oh, didn't we find that when we did the reflection? That your intercept is now negative 1, 0. Right? The range doesn't get affected in this. Your asymptote didn't either, because that's the line that we did the reflection over, the x equals 0 line. Remember, vertical lines are x equals, horizontal lines are y equals. When we did exponential, we were y equals 0. When we did the inverse, we interchanged the x and the y, so that y now became x equals 0. It just gave us our other axis. Okay. Okay, the next one has a shift horizontally. It's next to the x. Next to the x goes the opposite way. Next to the x says, move this 3 units this way. Keep track of this guy. It's going to move 1 to the 0, to the negative 1, to the negative 2. Negative 2, 0. Now also, notice we have a y-intercept. Now this was my x equals 0. This is moving over 3. I am now x equals negative 3. My domain was 0 to infinity. This is moving over 3. There's my new domain. Makes sense? That's why I think it makes better sense to do them by hand than it does on your calculator. So on your calculator, you're not going to see the change in the domain and the asymptote as easily. To find your x-intercept, set your y equal to 0. To find your y-intercept, set your x equal to 0. And you can do this part right on your calculator. Technically, this is what I'm looking for. That's the exact value. In pre-calc, we tend to round to 3 decimals. Everybody's good with this? Okay? Next one, where's my shift?
5 units down.
5 units down. I used all the LNs just so that you see there's no difference than your log ones. 5 units down. Same thing, but now we shifted down 5 units. We don't have a y-intercept because we didn't do any horizontal movement. So your domain stays the same, your range stays the same, your asymptote stays the same. The only thing that changes is your x-intercept. And set it equal to 0. Do we kind of see the same thing happening over and over? Okay. And this is the last one. We did 2 things. We did a horizontal shift to the right one, and then we did a vertical shift up 2 units. So to the right one is changing your asymptote. It used to be x equals 0, we added 1. X equals 1 is your asymptote. Your domain was 0 to infinity, we added 1. 1 to infinity. And we have to find a new x-intercept. Take a look at these. Lazy, what's the problem? But they work off of your basic log. Your basic log, no matter what log I give you, looks like this. Because, I was going to use a color, but because this was your basic exponential curve, wasn't it? So if all it is a reflection, all your logs work off of this. Whether I say log base 2 of x, log base 10 of x, ln x, they all look like this. Now the only difference is, for our sketch, they're going to look like this. The only difference is, like if this is a log base 2, a base 10, because there's no 10 here, but it's understood to be 10, will just come a little closer here and a little closer here. It still has the same attributes. The domain is still the same. The range is still the same. The x-intercept is still the same. And the asymptote is still the same. The only difference is, in reality, it comes a little bit closer to here. Now, the reason I'd rather have you draw these and put them in your calculator also is, remember with your exponential ones, it looks like your calculator kind of stops here. Well, it does the same with your log. It looks like it stops there. But it really doesn't. It rides that axis. So when we say sketch, I just want you to give me a basic sketch. Just give me a basic sketch. All right, we're going to sketch a little bit more tonight after we go through these rules. Are we okay with these? Okay. So if you kindly go back to your classwork from yesterday, we're going to go through your 3 rules, and I like to call them 4 rules. For dealing with logs. Okay. Now, because we say logs are exponents, they have the same characteristics as an exponent. When you were multiplying your like bases for your exponents, what did you do to your exponents when you multiplied like bases? You added your exponents. So when we do a product for your logs, they're like exponents, we're going to turn it into an add. So your product says just take the 2 factors and separate them. Turn it into an add. Regardless of what base it's in. I could do base 2. I'll say x times y. So log base 2 of x plus log base 2 of y. I could do ln. Regardless of which base we use, it's the same thing. Think of an exponent. When you multiplied your like bases, what did you do? You added them. So now, with our exponents, when we divided our like variables, what did we do to our exponents? Subtracted them. So when you divide, which is your quotient, you're going to turn this into a subtract. Simple as that. Regardless of whatever base it is, you continue with the base or the ln. Now we don't need to say base 10, but I put the 10 there so that you could see it could be any base in your log. If you do log base 7, x over y, this is a quotient. We say log base 7, x minus log base 7, y. We just separate it into a subtract. Numerator minus denominator. Okay? Now we have one more rule called the power rule. And this is the one we use a lot because this is the one that helps us get our exponent to come down. And the power rule says, take your exponent and just bring it down in front. So I like to add one more rule in here. Right before this, I call this my root rule, or my radical rule. Sometimes you have a radical sign. You have to get that radical out of there and make it into an exponent before you can bring the exponent down. So here's the way this works. In the square root, there's a little 2 in the index, right? And there's a little 1 out here. They're understood. We don't use them. To make a fraction, fractional exponent, you keep this one here. See where x is raised to the 1? And then this is outside. That's the 1/2. So you're going to turn this into a log base 2 x to the 1/2. Now you can use your power rule and bring it down. So what would I have if I was a cube root of x? What would my exponent be? 1/3. What if I'm the 5th root of x squared? What's my fractional exponent? 2/5. Keep this guy here. Keep this here. He's what goes on top. He's inside of this. He goes on the bottom. So you're going to convert your radical into a fractional exponent first. Then you can bring it down. Okay? Okay. So let's try some of these. We either expand or we condense. Expanding means we use our rules and separate them out. Condensing means we have all our rules in place and we bring them back to one term. Okay. One term is many factors or quotients or whatever we need to do. Always first check when you, well, we'll talk about bringing them back in a second. Alright, so now, doesn't matter what base I am. This is what I'm looking at. What operation is going on over here? Multiplication. When we multiplied by bases, what did we do to the exponents? Added them. So this guy is going to turn into an add. So we're going to separate them by factors. Do that first. Okay. And I'm good to go there. Does anybody see anything else that we could do? Exponent. This exponent says power rule. Bring it down in front. Like a Power Ranger. That rule is very powerful because that's the rule that helps us solve your log problems. That power rule is the rule that helps us do this. Well, we can't drop 7 to a base of 2, and we take the log of both statements. This is the guy that brings this down. So now we can divide both sides by log 2. That's a very, very powerful rule right there to break down your power law, to bring it down, your exponent. That's the only thing that helps us get that down there. Now, when you're looking at something like this, think the reverse of order of operations. My first thing I would do is plug an x in, do this mess over here, take the square root, and then divide. Go backwards. Undo the divide first. So when we divided by bases, what did we do to the exponents? Subtract. So first thing we're going to do is turn this mess into a subtract. Okay? Now, notice I have a radical there. I can't use my power rule to get rid of the radical and replace it with an exponent. So I'm going to take this guy out of here. What's my exponent on this? This is a 2 in here, so 1/2. Good. Anything else I could do now? No, let's leave this. Bring down your power. Excuse me. There's nothing we can do to this. We leave it like that. That's like it's an argument there. There's nothing we can do to that. It's not a multiply, it's not a divide. It's just an argument in there. So we leave it like that. Make sense? All right. Let's take a look at condensing some. We go the opposite way. When you go the opposite way, the first thing you want to do is make sure the log word is by itself. But it's got something in front of it. It's got a 1/2 here. Where did this 1/2 come from? The exponent. Good. See? Bring it back up. Bring this 3 back up here. So, log, you don't have to write the base 10 if you don't want to. As to the 1/2, well, what is that? Radical. That's my square root of x. And what were we doing when we added those exponents? We were multiplying. Bring this down to a product. This is where you get one log word. Then you get the product of this times this. That's what we started with. We separated it. We got rid of our radical. We brought down our exponents to expand it. Now we turned around and we condensed it all back. One step at a time. I know some of it's a little redundant in writing the steps. If you find you have your exponent there and you can automatically pull it back up or change it to a radical, I'm fine with that. So this guy, I've got an ln, but this guy has something in front of it. My 2 has to come back up. What were we doing when we were subtracting those exponents? Dividing. So bring out one ln and give me a divide. Good? Is that the end of that? Yeah, that's the end of that. Okay, what I want to do is just go over. I'm going to leave you to do some of those, but I want to do a few more of these. God bless you. I'm going to leave you. Okay. Change a base. You can only put a log base 10 in your calculator. So yeah, if you have your log change thing, you can absolutely go into your y equal, and you can do this guy in here. You can put a 6. You could put an X. A second window, or you can go to math. If you go to math over here, and you keep going all the way down, after summation, you'll see your log base. Yeah, if it's crossed out, give them to me, I'll reset them. Now, okay, I'll take your calculator. You can also do this in your y equals. So math, write in your y equals. There's my base 6. There's my x. Okay, I'm just going to do a zoom 6 to get back to normal. It's a regular curve. If for the time being, and you don't have one that has this, where you have the 83 calculators, the 83s do not have this function. So we're going to make a line like this, and we're going to do the one that stays underneath, stays under.
What does that mean?
It's just changing the base from 6 to a base 10. It's a formula. You see the 6? Keep that in the denominator.
Oh, it's on the line.
Keep it under the line. See the line? That's your denominator, that's your numerator. But they both had to be changed to log base 10. Now you can absolutely put that in here instead. I'm going to put it in my first one. So I'm going to say log x divided by log 6. And see if it gives me the same graph. Oops, I had a log x in there. So, same graph, right? So change a base, you can do it that way. All right. Now, before regardless of what base it comes in, we get the same look. It's going to look like this. Everybody write down these attributes. Your domain is from 0 to infinity. Yesterday, didn't we try taking the domain, the log of 0, right? It doesn't work. The log of a negative doesn't work. The range is all real numbers. Your x equals 0 line, which is your y-axis, is now your asymptote. And your x-intercept versus your y-intercept is 1, 0. All your logs, whether they're ln's, base 2, anything, works like this. This is the sketch we'll make. These are the attributes we'll give them. Of course, as the base gets larger, they ride a little closer to the axes, but for our sketch, this is fine. So now, let's take a look at this guy. This is my parent graph. We just graphed it, right? What's happening? If I plug in an x, what's this guy doing first? Horizontal shift which way? To the left. That means this guy has to move from 1, 0 to negative 1, 0. Well, if it moved, did my domain change? Because my domain was from 0 to infinity. So yes. So I'm going to add 2 to that guy. Okay? Sorry, subtract 2. We're going the other way. Subtract 2 from that guy. Plus 2. So we went left 2. I'm going to subtract 2 from this. My asymptote was here. That had to move too. I'm going to subtract 2 from there. My intercept also had to move. I'm going to subtract 2 from there. So my new domain right now is negative 2 to infinity. Did it change my range?
No.
No? My all real numbers was not affected. We said my asymptote also moved. And now my new point was negative 1, 0. Was it negative 1, 0? It was negative 1, 0. So far, so good? Okay. Then I move out here, and I notice this negative out here. It's not next to the x, because the x is here. It's next to my y. So I say to myself, if my y goes from positive to negative, where is my reflection? Oh, good. A reflection over the x-axis. So this guy gave me a horizontal shift. Let me just write this out. Left 2 units. And this guy gave me a reflection in the x-axis. So all I have to do now is go like this. So let me see what changed. Did my domain change? No, because well, from the original, no, from the one that we just did before this, that we're still on the same problem. So it's still negative 2 to infinity, right? Is my asymptote still at x equals negative 2? Okay. Did my intercept change? No? And my range, did my range change? Range is all real numbers. Yes. I didn't solve it algebraically yet.
I know, but
We'll do that in 1 second, because I'm going to do it off of this one. I just wanted to get all the transformations down. And this is where my asymptote is here, not here. Sorry, I was just drawing a line as a reference to where I moved to. So that might have looked a little confusing there. Okay. All right, now, we're good so far? Now, Venetia just said, what happened to your x-intercept? Why didn't you solve that algebraically? Yes, we have to solve that algebraically yet. So my x-intercept said set y equal to 0. Go to this equation. Set y equal to 0. Okay, again, flip it around. If it's easier, flip it around. So convert this to an exponential equation. Log equals exponent. What's the base of my log? 6. What's my exponent? 0. Don't forget you have maybe let's put a -1 out here for now. Equals what? X plus 2. You with me? What's 6 to the 0? 1. And 1 times this would be what? What do I do with my -1? -1. Oh, let me see what happens here. 1. So something is off. Hang on. Oh, let's just get rid of that. Let's get rid of this negative ahead of time. Let's divide by a -1 here and just get rid of our negative ahead of time. So we can keep it like this. And then this subtract 2. So there's our -1. There's your intercept. Now, what happened here when we moved to the left? What else did we now have? My original graph didn't have a y-intercept because that's where my asymptote is. But doesn't my new graph have a y-intercept? So, when I solve for y-intercept, what do I have to do? Set x equal to 0. Good. So let's come back here and set x equal to 0. I'm just plugging this in. Now this you have to do on your calculator because we're in the log base 6. Okay, so that one you're going to have to do on your calculator. Now notice, where is my y-intercept in this? It's my green line. This is my green line here. My y-intercept is going to be negative. So you're going to put this whole thing like this right into your calculator. And give me 3 decimal places. Okay. And so doesn't that make sense where I am? I'm below the line there. Right? Make sense? Yes or no? I have out there with my exponent. Put it in front. Great. Put this guy in front. There's my power rule. So let me ask you, when we did this, and then we did this, what did the number out in front do to my function? It actually made it stretch, right? We had a stretch or a shrink. So we either have a stretch if it's greater than 1. We have a shrink if it's between 0 and 1. Okay, change the distance to 0. So this is going to have the same effect on my log graph. It's just a little harder to see when you do a stretch or a shrink on the log graph. But this tells me a vertical shrink by a factor of 1/2 of 1/2. Now, let's take a look at that. I'm really not sure what it does. I think this says a vertical shrink. I'm not really sure what it does. Put it in your calculator. Put the 2 in together. Confirm it on your calculator. I like you to walk through because this one's not going to change your domain, your range, or anything else here. So let's just put this so that you can see what's happening here. Log base 3. So maybe I want to put my log base 3 out here. My parent graph, my core graph, whatever you want to call it. And then down here, we're going to do 1/2 of the same thing. Okay, see what it does. Here's my original. Here's my new graph coming in. Remember, this is a shrink. It changed my distance from 0. It's very hard to see. Your calculator really can't get any more exact in this area here. But it's like if you change the number a little bit. You shrunk it down. You shrunk the distance. Remember with the parabola how it flattened it out? But that was your shrink. So it's kind of like the same thing. That flatten this out look to it. All right? All right, so tonight